Welcome to you all. As you know, today is 11th of February, so it's International Day of Women and Girls in Science. And at ICMAB, we like to organize talks about women in science to inspire all our people. And this year, well, we invited Dolors Herbera, who has been professor for more than 30 years at the University Autónoma de Barcelona in mathematics and algebra and many other things. She has also worked in different universities, for example, the Rutgers University in the USA, as a Fulbright postdoctoral fellow. And she has been visiting professor in Italy, Germany, Norway, the Czech Republic, Mexico, Hungary, many different countries around the world. Her area of research is, in fact, algebra, which is topics, and she, in fact, works with topics close to which of those Emmy Noether worked during her life. She has more than 40 articles and has been speaking in many different conferences. And currently, in fact, she's the president of the Catalan Society of Mathematics. She's also a member of the scientific committee of the Barcelona Graduate School in Mathematics, and the secretary of the Spanish Committee of Mathematics. So apart from being professor and researcher, she also takes part in different organizations to disseminate and let people know what mathematics is and to spread this knowledge. So yeah, we're very happy to have her here today, and I hope you can enjoy the talk. After the talk, you will be able to ask her some questions if you want using the chat. I remember you though that at 1 o'clock we have to stop because we have the League of Women Scientists after that, which will be a contest that we also invite you to participate. So Dolors, the stage is yours. Thank you.
Okay, thank you, Anna. Thank you for this kind introduction. So let me share my screen. So thank you for this opportunity to celebrate with you this September 11th, February 11th, this day of the women and girls in science. So just a comment on all these positions that let's say bureaucratic positions, or that Anna was taking about. I don't know, it's just a reivindicative comment, just because of the journey we are in, is that, okay, it seems that women, we need to make ourselves present in this kind of positions, because to let us being known, so that, okay, actually I started this kind of bureaucratic work like 3-4 years ago, and when you start, you never end. But okay, it's nice, and it's also it's another way to contribute to the mathematical community. Okay, so let's go for our topic. We are going to talk about Emmy Noether. Emmy Noether is a very important figure in mathematics, and very prominent. It is funny because the physicists know her because of the Noether theorem, and mathematicians practically ignore the existence of the Noether theorem. So they know it for her work in abstract algebra and for what I was remarking here. So let me spotlight here. Okay, for what I was putting as a subtitle, of introducing abstraction in mathematics, in algebra in general, and in mathematics in algebra in particular, and in mathematics in general. So that was her big contribution, according to mathematicians, to that, and then having many results and important work done there. So let's go to explain a little bit her life. Okay, here is my first slide. So this story starts in Erlanger. Erlanger is, you can see here in the map, is a city here in the north of Bavaria. And she was, born in a Jewish family. She was Jewish, and this is going to be important for her in 1882. Her father was Max Noether. Max Noether was a professor at Erlanger, First, he was doing, well, not really the PhD, but at least going the PhD title, the doctor title. I mean, doing PhDs is a concept that has evolved in life. I mean, in times. No? So that's, and essentially he was working in something called algebraic geometry. And it's okay, maybe not so well known as her, but it's a known person that has doing important work in mathematics. No, sorry, that was have a too sensitive. Sorry, here, have a too sensitive mouse, I think. But okay, here are the brothers. She was the elder, and then she had two more brothers. The second one was working in chemistry. The third one, no, Fritz, was also a mathematician, and then I think the younger one died quite young. I don't know anything. So the family of Max Noether were working with iron, and the mother, which I was not able to find a photograph, was from a quite rich family, no, wealthy family from Cologne, as Emmy Noether. But she died relatively young, which also I think it was an important thing in Emmy's life, no. So here I put the name of the brother. Fritz is this brother that also was a mathematician. Okay, so that's here we have Emmy born in 1882. So then, okay, now I cannot move. Okay. Then until she was 18, no, as I was seeing here, she followed the path of at that time the normal middle class girl. So 18 means okay, the beginning of the 20th century, no, 1900. Growing up, so she was growing up in, okay, not a normal family, so an intellectual middle class family, but with intellectual life, no. So family, no, the father being a professor at the university, no. She studied, okay, German, arithmetic, some piano lessons, but she was not very good at piano, no. And it seems that she loved dancing, no. So in this 1900, no, she takes the exam to become a certified English and French teacher for the Bavaria state, and this at that point, no, seemed that would be the end of it. No, that was the normal life for this type of for women that at that time, no, so get some studies, then get some job, and then probably get married, forget about the job, and take care of the family. But okay, something happened, no? So something happened, and at the same time, no, this year, she decides to do something very strange at that point. That was to enter the Erlanger University, no, where his father was working. Sorry, here you see the seal of this Erlanger University, no, but. So this was representing a big difficulty, no? Because in 1898, there's the Senate of this, no, there's this Erlanger, no, Friedrich Alexander Universität Erlangen-Nürnberg, that's the official name, also right now. No, they claimed that admission of women is a measure that would overthrow all academic order. So was no point, no, so no possible to admit women. Okay, I suppose that still she had some influence. So because the father, no, was a professor at the university, so she managed to attend classes for a couple of years. I suppose from what I have heard that this had to do because her brother Fritz was also starting mathematics, because probably she was able to attend classes, but also accompanied by a man. I mean, that I suppose, that's that should be also a point. Also, at this point, she had to go over another difficulty, because the studies of women were not the same as the studies for men before entering the university. So that they were not allowed to go to the gymnasium. And then to enter the university, to really be able to enroll, they had to pass an exam, the post-maturity exam, or what we call here a selectividad. So she had also to prepare that exam. And she passed that exam in 1903. Then she was, But at that point, what she decided to do is to spend the next semester at Göttingen, the next semester at Göttingen, which was a little bit more liberal with women. No? So here we see a photo of Emmy. That the only data I was finding that it was before 1910. I have seen somewhere else that it was probably 18 years old, so that maybe it's this 1900 year, I don't know. So, but in any case, she looks pretty young, no? Here. Okay, so we have her at Göttingen. Let's see. So, okay, here. Now it's the time for this, no? Göttingen. So Erlanger was, so as you will see, the professors at Erlanger were also reputed mathematicians, but Göttingen at that time was really the Olympus, no, or the Mecca for mathematics and physics, no, and actually in that semester, what she was able to follow courses by David Hilbert, Carlos Schwarzschild, that Schwarzschild, sorry, I think that's a physicist. I think he was an astronomer, and also belonging to a family of astronomers. No, that the father or son was always a famous astronomer. A very important figure that we will also meet later on is Felix Klein, no, and Hermann Minkowski. That's another famous mathematician for his work on number theory and also for the work on geometry, and that's really well in mathematics. These are really well-known people and people you keep finding results. No? Okay, so that was her team of professors for that year. But it seems that for some reason, then Erlanger allowed to enroll women, really enroll women in the university. So she went back to Erlangen in 1904. Comments that they say, that something that could have influenced this decision to go back to Erlangen, because let's think that Göttingen at that point was more prestigious place than really Erlanger. Is that also, okay, don't forget she's a woman, and her mother was not in good health. So probably going back to take care of the mother or doing some job with the family was also an important reason to go back. And there she goes. She continues studying mathematics, and she's not also laureate in mathematics, no? Okay, here I was only a woman in a group of 46, of course. That was the situation, no? But also she went for a PhD, and she was awarded the PhD degree on July 1908, and the supervisor is Paul Gordon. Paul Gordon was a person that was well known to be incredibly good with computations, and so everything he was doing were lots of computations. Here I am showing, I put also Gordon, and here I put also a photo of Albert Clebsch, because maybe you are familiar or you have heard of the Clebsch-Gordon formulas or Clebsch-Gordon coefficients, for some types of representations of groups that I think are related to the spin, actually, to the definition of the spin, and they are important in physics. So just to make you think that maybe at some point we are talking as Erlanger are not as such important place as Göttingen, but really also with relevant people, and also maybe we are going to say, okay, Gordon computes a lot, but okay, maybe he computes a lot, but he computes makes a lot of sense, So the topic of the thesis was something called invariant theory, that I am going to explain a little bit what it means in a little while, And well, this is the thesis of the title of the thesis, It was published on what's known. This is known as the Crelles Journal. It was founded by Albert Crelles some years, had been founded by Albert Crelles some years before, and that's still right now, it's a very prestigious formula. And what we see on the background, is a table of, I don't know, 300 something invariants, that she compute with some formulas and incredible, So a strong computational work, And she, after that, because she was absolutely not, so all what she did in mathematics after that was kind of opposite to this heavy computational machinery, that classified the work like by her this of mist. And mist is this case is a German work, and according to the Google translator, it means damned. No, so that's not she was not satisfied of the work done in the PhD thesis, no, of the kind of work, no, and okay, so what was going to be the mother of modern algebra was going to work in a different direction. No, she will really completely switch direction. No? So let me now go into my more mathematical part of the talk. To talk about a little bit what's invariant theory, and essentially, let's see, okay, how the symmetry is formalized in mathematics. No, the symmetry is formalized in mathematics with the idea of groups. No, so here I put nice couple of these nice pictures you may find on internet, people doing wonderful things and saving a lot of work for presenting this kind of talks. No, so this is for example, this one of on the left, no, is the group of the movements, no, that gets okay. So the idea of symmetry, no, is abstracted, no, in the idea of groups, no, groups that are moving figures, no, groups that so movements that are moving figures, no, and as many movements you can do, more symmetry you have, no. So for example, this is the idea that we see here, no. So this concept of symmetry, which is also related with beauty, no, and harmony and that, no, had this has this formalization, no, in the terms of mathematics of this action of this movement. So how you can rotate or well, here are rotations or reflections, no, or no, without really apparently changing them, no. So here is the idea of the square, no. So the square, of course, what are we doing, no? We are adding the names to the vertex, no, because this way putting a label in each vertex, realize what happens. But for example, when we move it 90 degrees, no. So when we move it 90 degrees, so A has gone here, no. So that's clockwise, no. A has gone here, B has gone, the vertex B has gone here, and C has gone here, and D here, no. So otherwise, without these labels, we wouldn't distinguish the square, no. So then we have, so these 4 letters, no, starting always on this vertex, are changed to these other 4 letters, no. So if we go on and we move 90 degrees more, no, so then we see the same square, but with our labels, we notice, no, that original A, B, C, D has gone here, no, and okay, the next thing is this, no, 270, no. So then we have reflections with respect to axes, no, that go from the mid of one side of the square to the opposite one, no, this one, and then the diagonals, no, give also some reflections, no, and we can distinguish, no, these movements, no, we are doing, no, but the labeling these things. No, so notice that we can just describe everything we have done with the square, just keeping record of how we are permuting these 4 letters. No? So this tells us, no, that this group, no, that this group of symmetries, no, of a square is just a group that we can see inside of what is called the permutation groups of 4 elements, which in this case we identify with the way of how we can change the order of these 4 letters. Okay, these are not the possibilities for the permutation groups of 4 letters, so these are just some that could be, no, correspond to the movements of a square. Here, if we go to the cube, no, and we try to do the same thing, okay, we have the same kind of rotations, no, so these rotations that go from from the mid of one face to the mid to the center of the opposite. So mid means the center. That is sorry. So the center of a face to the center of the opposite face. No, so you have one here, no, two here, and then the one in front of us and the one behind. No, that it's a little bit strange in the drawing. No, so here the other axis of rotations, no, go from vertex on one vertex to opposite vertex, for opposite vertices, for more of them, no, and here this thing, no, these are twofold axis. This is going from the mid of one side, no, to the middle of the other opposite side. No, this gives another set of rotations. No, so then we have no centers of inversion, and then also the reflection, no, with respect to, now it's three-dimensional with respect to a plane. No, so that all together gives 48 elements in the group. I don't know if you are seeing it because Zoom is covering me a little bit of that. It's a total of 24 rotations, no, and then the rest are these ones here. Sorry, I apologize. No, and one thing to trace, one way to trace or to describe this group is that if we consider the four diagonals of the cube, no, so going from one vertex like this one to the opposite one, what these movements do is all the possible permutations of the four diagonals. So in this case, actually this group is isomorphic completely now sorry, I apologize. So sorry, to the group of permutations of the four diagonals of the cube. So this is the full group of permutations. No? So how come this idea of explaining symmetry in terms of groups? How come to how that it appeared? No, so it appeared. No, it was formalized. Sorry, it seems that I can move. I keep moving the slides whenever I am not interested, but when I want to do it, I cannot. I have some problems, no, to say what. So I should improve about this. Sorry. Okay. So this idea of reflecting the symmetry on the actions of the groups or in relation with the groups came from solving actually what at the beginning of the 19th century was classified as the most outstanding problem of algebra, and that has been going on for really a number of years at that point. No? And this was to find formulas. So formulas with radicals depending on the coefficients of the polynomial for the solution of a polynomial equation. Okay, we all know, we are very familiar with the formula of degree 2. The formula of degree 2 was known, okay, I think at least a special case is known from the antiquity that the Egyptians, Babylonians it seems that they made some special computations already with that. And it's a formula that we all know very well right now. So then degree 3 and also degree 4, there are formulas. These are, sorry, there is this, forgetting because there is another name here, some Del Ferro, there's some Italian people, no, these contributions, Del Ferro, also Tartaglia, and then also Cardano, which published this book, the Ars Magna in 1845, no, that gives you an idea of which, no, when we are talking about. Also, there are funny stories about them because they were fighting each other and telling, okay, I can solve that, can you solve that? No, so they were sending not that friendly letters one to the other, no. So they are kind of fighting within each other, no. But then that was it, no. In 1545, no, this Cardano publishes these solutions, no, of degree 3 or degree 4, no. But okay, what about degree 3? And the degree 5, no? So and so on, no? Why can we continue? And so the amazing solution, or to that time, because everybody was convinced that it was just a problem of, okay, trying, and then they would manage to solve it. No, so if you can solve degree, okay, I am forgetting about degree 1. So okay, we can solve degree 1, but if we can solve degree 2, degree 3, or degree 4, why not degree 5? No, so and actually this took a while, no, to prove that really is not possible. No. And then the first one that managed to, so the first one that imagined, no, that was not possible was actually Ruffini. Ruffini in Bologna. Actually in 1801, more or less, he wrote a proof, no, that it was not possible to solve the quintic, no, but there was an error, no, the ideas were not bad, but there was an error, no, and actually he was a medical doctor in Bologna, and there was an epidemic of typhus there, and now we all know what this means. So they had a pandemic, and he had to work with that, and actually I think the matter was kind of forgotten to him, no. So then the next one that really seemed to give a complete proof, that the proof that really gave a complete proof that the degree 5 equation, no, there was no solution, no, with radicals, no, of the degree 5 equation was Abel, no, Abel, that was actually in the University of, at that point was Christiania, that's what we know right now as Oslo. In 1815, he has a paper in that, no, a famous paper, famous result, and the one that become also most well known because for that, probably that gave also this proof that it was not possible, and also developed or give the clues to develop a deep theory about the problem was Évariste Galois. And he wrote his paper, that's the famous story, that he died in a, I don't know, in a duel. I don't know sorry, I don't know the English term. No, so these things, no, that they were okay, two people, no, that shooting each other because some honor thing, no, it was political business. So here there were the revolutionary people, no, French people that kept the ideas of French Revolution in front of the conservative monarchic people, no. So he was from a revolutionary family, and he wrote. It's famous that he finally wrote his final notes the day before the duel or the fight, the pistol fight, and left over there, no. And here I put this someone, no, Cauchy, telling him he was the bad guy, but was the bad guy because everybody, no, all these three people kept in contact with Cauchy and sent his writings to Cauchy, and Cauchy seems kept losing the writings of these people, no, and forgetting to answer them, no. So probably Ruffini, no, I was reading yesterday some comments saying that, okay, Ruffini, if Cauchy answers back to him and tells, look, this is wrong, probably Ruffini would have solved the problem, and Abel, okay, she has some comments saying, okay, these French people are very difficult to contact with, no, and okay, Galois also has some nasty story around that, no. So okay, so Cauchy did lots of things in mathematics, but at some point was not that friendly. So let me now go from here, and let me show me my more mathematical part of the talk, not to explain you a little bit, what this symmetry in roots of equations mean. So, okay, so let me start another share. I have to wake up my iPad. Here we go. Okay, you are seeing. Sorry, now I have to open. Sorry. Here we are. No, symmetries in polynomials. No. Okay, so as we are assuming, no, that we have this, no, polynomial like this. I am assuming it's monic, no, because otherwise things just get complicated, no. So here I have the decomposition in n roots, no, and then if we multiply, this part, no, so we get this kind of expressions, no. So the coefficients, no, these coefficients here, no, these coefficients, this corresponds to this, okay, this corresponds to this, no, and so on. So notice that this is just the sum of the roots, No? The second coefficients correspond to all the sum of products of two different roots. The coefficient, no, the next one is sums of products of three different roots, no, till the last one that correspond up to sign, no, to the products of all roots, no. So, and forgetting about the signs, we set this notation, no. This notation, no, the S1 is the sum of the roots. This is the sum of products of two, no. Till Sn is this the product of n of them, no. The order, no, so here things are commutative, no, so the order in which we write, no, the roots, or in which we write this decomposition here does not matter, no, so these expressions we get, no, for the coefficients reflect this kind of symmetry, no, that the order that does matter, no, and what we are saying is that they are symmetric with respect to this change of order, no, so if I make a permutation of the roots, the expression of these things never change. So that's what I am considering here. No, so think the generic. Now we are going to the generic case. No, so for example, this don't think they are in anywhere else, or they are in any concrete place, that they are just kind of indeterminates. No, and here consider these polynomial rings with coefficients. Okay, K is a field. Think whatever you want. What is or C or rationals or your favorite field. No? You consider this polynomial ring. No? For any reordering of the variables, that is for any sigma, this is a notation for these permutation groups. No? So this is the possible reorderers of n objects. No? These n objects right now are these variables alpha 1, alpha n. No? Then the group of permutations of alpha 1, alpha n. So let me notice that here there is a parenthesis missing here. Sorry. Here. No. No, we have a map. No, that so whenever so these permutations of alpha 1, alpha m, I can extend to a map defined over the polynomials. No, so we consider any polynomials in these variables alpha 1, alpha n. I could make it correspond, no? So putting in the first place what is sigma of alpha 1, then sigma of alpha 2 to sigma of alpha n, no? So then the symmetric polynomials I was talking about are the invariant polynomials under this, this is called the action of the group Sn, no? Then the fundamental, no? So here there is a theorem, the fundamental theorem on symmetric polynomials say that this so this is the set of invariant polynomials. This is the notation. No? These are just polynomials in this S1, Sn we have defined before. No? So I remind you that S1, Sn, no, are precisely these expressions. No? So here this means no, that, so this is to say, no, and this is really again polynomial ring. No? This is to say that any symmetric polynomial, so any polynomial that remains invariant, no, when I change the order of the variables, no, and that changes the expression, can be written in a unique way as a polynomial in this, what these are called these expressions, the elementary symmetric polynomials. No? So that's a kind of results on invariance, no, and that's the symmetry that we have. No. So of course this way, no. So if this we have started here, I have started saying, okay, this we can think is a way of moving the roots. But if we are thinking in this generic situation, no, this we can do any possible permutation. But now, in general, no. But of course, the symmetry of the roots of the polynomials should depend, no, on the context where the roots live. No, I was saying, okay, this field, this K, no, think it's whatever you want. I was thinking the alpha 1, alpha n were variables, no? So there are no relation between them. But of course, the real roots of polynomials we are interested in are not like that, no? So in general, after all, it's called the Galois group of a polynomial is the group of symmetries of its roots, no? And then what we have seen is that generically, no, if there are any roots, the Galois group is a subgroup of the group of permutations of an element. No? So that's, no, we can see it inside there. No? But how does this context, no, where the roots live matter, no? So for example, no, in a well-known case, no, so if we take real polynomials, the roots of any real polynomial lives in the complex, no, in the complex numbers, no, because that's the fundamental theorem of algebra. And over the complex numbers, no, so these permutations of roots, what we have to, what they transform is in automorphisms, so maps from C to C that respect operations that fix what we are starting, no, that fix the field or the real numbers, no. So, and there are only two of such automorphisms, no. One is the trivial one, the identity, no, and the other one is the conjugation, no. So really, the Galois group of the field extension, no, of or into C, okay, no matter is only has two elements, and then these two automorphisms, how they reflect, no, in the behavior of the roots of the real polynomials, no. The symmetry is reflected with this thing, no. So if we have a polynomial with real coefficients, no, we have that if they have a complex root, no, then also the conjugate is a root, no. Then with a little bit, I know it's a vague idea, no, but let's so that the idea to prove, no, that the quintic had not a formula by radicals, no, is that being able, no, to write the roots of an irreducible polynomial in terms of radicals. So here it makes sense to think about over rational coefficients, no. So then, no, irreducible over the rational. Then you want to write the solutions in terms of radicals of these coefficients of the polynomials. No, this is characterized by a suitable property of the Galois group. And this generic thing, sigma n, no, does not satisfy this property for n bigger or equal than 5. No? And this property of that sigma n has when n is equal to 2, 3, 4 allows to find formulas, but that does not have from 5 on, does not allow to find generic formulas, no, for a reducible, for the roots of a polynomial, no. And this was the idea that took, no, this was the invariant that needed to be formed, no. Okay, that was, I was showing you, this was kind of first part of the 19th century. So after that, no, the idea of group and the symmetry reflected in groups was taking big part of the work of mathematicians on that, no. And then, for example, the general, no, invariant, no, the general invariant theory that was, no, that Noether was doing her PhD, no. In general, we have a group, no, K a field. Usually this field was C, no. B a K vector space, then a group morphisms to G to the invertible transformations of our vector space, no. This is what is called a representation of B, no, and this can be extended to an action on G on K of B, no. So this can be identified. This is like if B is n-dimensional. This is as we are talking of the, so this is, so if you want the symmetric tensors, but can be identified with polynomials in n variables, no. So there is a formula to define this, to define this action, no. So that's acting on the, no, that's the way the group acts on the moves the variables somehow, no. And then one of the main problems of invariant theorem was finding the fixed elements, no, about G, no. And the first question is whether this is finitely generated, no. And Paul Gordon was working a lot on that. He had proved in general case, several particular cases it was finitely generated, and then they were doing these tremendous computations, like in Emmy Noether's PhD thesis, no. So then Hilbert came, and actually this was his first paper, no, and gave an affirmative answer by absolutely abstract and non-constructive methods. No? And there is this famous sentence of Gordon saying that, okay, that was not mathematics, that was really just theology. No? So that was not real mathematics. But okay, things imposed, no, and actually this was really the striking for this result for the invariant theory. Here I put an example of what the kind of things Hilbert was proving. No? So polynomials on two variables. This is just a notation for the group of two elements. So the action we are considering is just changing side. So then the fixed elements, the fixed polynomials by this action, okay, should be polynomials of even degree. So this is like generated by this. No? So this we see in C of xy. No? So this is the subring of C of xy. No? And this, so the point is, okay, the number of invariants is this, but here it's also important. No? So there are three generated by three invariants, but it's important also the relations between them. Between the elementary symmetric polynomials, there were not relations, but in general there are. No? And this was part of the Hilbert's thing. No? Hilbert's thing was showing that these rings of invariance could be shown this way. No? And the relations, that's what's in here. No? The relation and something that's called the Hilbert basis theorem shows that these relations are always finite. No? So here this notation means that the relations are always multiples of this one. No? So if you think that A means x squared, B means xy, y squared means C. No? So what we are saying here, okay, what goes to zero? To zero goes AC, so that's x squared, y squared. No? Sorry, I can write this. No? So that means that the relation is x squared, y squared, minus, if you want, xy squared. No? So that's something that if you change signs of the x goes to it becomes to zero. No? So when we make this so that's a relation that type ABC this variable should have if they should come from the subring of the polynomial ring. This thing. Okay, so that was the classical invariant theorem, but there were many more things that this kind of following generation to the solving of the resolution of the quintic equation was doing with groups. So something very important was, for example, going on in geometry. And actually it was Felix Klein, who was also a professor who was very young, started to be a professor at Erlangen also, and he made what is called he proclaimed, started to work on what is called the Erlangen program for geometry. The geometry from the Euclid's elements is a rigid geometry. It's a rigid that talks about figures, fixed figures, similarity between figures, axioms, and what Klein was proposing is that it's a completely opposite. So he introduced the movement in geometry, and the movement were the groups. So the geometry was determined, the space of geometry we are working with is determined by the groups of symmetries we were there. So for example, if we are interested in keeping down distances, we will talk about the orthogonal group. If we are just talking about parallelism, incidence relation, we will talk about the general linear group. So this is things like that. And here, let me call the part that comes with the famous Noether theorem. So, okay, I have explained you a lot, or tried to explain you a lot the discrete case, the discrete case of the group actions, mostly finite groups. But what about if we go to differential equations? So we polynomial equations versus differential equations. But what about if we introduce the continuity? So there was Sophus Lee, also a Norwegian mathematician, also working in Christiania, and a good friend of Felix Klein, had developed the theory of Lie groups, introducing this notion of continuity and of change there. And why not to study the invariance under that, the invariance under these differential equations? Okay, and then actually Emmy, after her PhD thesis, learned about these things, from Ernst Fischer, that we see here in the photo, when he was in Erlanger, and this was very influential in the story of the Noether theorem. So let me continue with the other part of the. So this is my mathematical introduction to here. I'm starting to be a little bit concerned about my time. So, and then this is, but maybe I am going a little bit too quick, but please do not doubt of stop me whenever you want. Okay. In the work of Emmy, we were here, PhD thesis with Gordon, many computations, invariant theory, that we have seen a little bit what we were talking about. Okay, what's next? So there is a first period of research, after the PhD thesis, and that goes to goes from 1908 to 1919. What happens in this period? Okay. From 1908 to 1915, she's in Erlanger, working in her research and also helping her father, which was becoming old with the classes. Of course, no economical compensation. She essentially continues with the PhD thesis topics, following Gordon School. And at that point, she advises to PhD students, she has important scientific interaction with Fischer, this Ernst Fischer, and that appeared in Erlanger in 1915, and she gradually was learning, from Fischer, this Hilbert's abstract methods. They were working together. They were writing postcards each other to talk mathematics. And this here, the image is an image of one of these postcards. What happens there, is that in 1915 her mother died, So and then she's invited to join Götinguen Mathematical Institute, of course with no salary, and also think that at that point the First World War has started, and many men were fighting in the front, So that's Unfortunately, the First World War is an important. It's historically very important for the incorporation of women as a workforce. And maybe the mother dying, so get free of some obligations, while this need of recruiting people, of recruiting professors, helped her to move to Göttingen. So he went to Göttingen. He had to pass an habilitation to become a professor. She was not approved because of anti-woman professors in the university comments that we will describe a little bit later. But she starts to be recognized as a mathematician. She enters this Circolo Matematico di Palermo and then the German Mathematical Society. And she attends meetings and she has an interesting. So she's incorporated to the community of researchers. In 1915, so Einstein had visited Göttingen. So Emmy went there on the fall. Einstein was visiting Göttingen on the spring semester, to make some talks about the relativity theory to the mathematics department there, And actually, when she goes to Göttingen, Emmy is proposed by Klein to work on the problem of invariance of energy, of whether energy should be invariant or how to justify the invariance of energy in relativity theory. So this was represented to explore the connection between differential invariant theory. And then she soon proves, this version, not that precise version of the Noether's theorem. So that this is published in a paper in 1918. So here is the first page of the paper. No, so every differentiable symmetry of the action of a physical system has a corresponding conservation law. Differentiable symmetry means the action of a group, of one of these continuous groups of Lie group, that we would say right now. No, and actually, no, there is this comment by Einstein, no, about this paper in a letter to Hilbert, saying that, okay, yesterday I received from Ms. Noether a very interesting paper of invariant forms. I am impressed one can comprehend these matters from so general a viewpoint. It would not have done the old world at Göttingen any harm had they picked up a thing or two from her. She certainly knows what she is doing. Okay, here I'm not completely sure what he means, if there are something that I don't ignore, but certainly he's liking her paper. No? However, okay, these results of Noether were published, actually there are two Noether theorems, no? And they were published in two papers. They, as I was explaining to you, mathematicians are not so much aware of this work. And also, in physics, it was really started to be recognized in the 50s. No? So for a long time, it was quite ignored. No? But now I think it's quite a standard and it's quite well known. And there are many developments out of that. So my idea is that's an important result, and then you can tell me better than I know. Okay, let's spend a moment with the habilitation process. No, that's to get the permission to become the permission to become a professor. No, so in 1917 they tried. No, again Hilbert was helping her to get the habilitation to be in Göttingen. And it seems, no, this is the translation of a letter that he was sending Hilbert was sending about that, no? And so this is the original letter, and here we see the translation, no? So if you read a little bit, no, does this thing, no, with regard to accepting women to teaching positions, the regulation of Frankfurt University are identical of, also it seems that they pretended to urge Göttingen to habilitate her by saying that she would move, no, they would lose them, no, and okay, they are answering that okay, the regulations are the same everywhere, and she's not going to be in Frankfurt because women are not allowed to be professors at the university, no, so that's the summary. So there is no need to do anything. No? So that was a negative answer. But okay, finally, no, so the war was already finished. In 1919, there was some relaxation of the norms, and she succeeded to be habilitated, but not to getting a salary until 1923, and of course not a salary. A small salary, no, not a real salary of a professor, no. Okay, so let me talk you about just a little bit about the second period of research. That was the period when she became the mother of algebra, no. She changes subject, so she goes directly to this abstract Hilbert methods, no. And actually, her work is giving form of how algebra is explained right now. No, so no computations. No, but what you should do is manipulation of ideas. No, so the school was kind of refounding, no, ambitious, kind of refounding mathematics. No, algebra and algebraic structures are the basis of all mathematics. Okay, this period is a little bit to construction and study, no, build tools, no, to language, no, to be developed later, no, and it became very, very influential very quick, no. She was at that time advised 9 PhD theses at Göttingen after she got the habilitation, no, and well, she was very admired from young colleagues and had an interesting, nice school. Here I have Van der Verden, no, what was one of his most known, no, students, no, that because he wrote this book, no, that was classical in algebra for many years, no, modern algebra. Then okay, let me talk a little bit about the third period. that goes from 27 to 35. No? So these abstract methods were developed, now we should apply them. No? Mathematical maturity, and also she starts to get strong recognition. No? So she starts to study, because the study first was kind of what is called commutative, was developing commutative algebra. She starts to work in something non-commutative, and with strong applications with number theory. There is an important visit to Moscow. No? So she had some sympathy, no, for the Russian Revolution. Well, apart that the Russian mathematicians are very good in general, no? So there is a very good school and it's interesting, but also there was part of that, no. And as a recognition, she receives this Alfred Ackermann Topner Award together with Emil Artin. And in 1932, she was invited to be a plenary lecturer at the most important conference of mathematics, no? The International Congress of Mathematicians, held every 4 years, where the few medals are decided. No? At that year, it was held in Zurich. No? So here you see the conference photo in Zurich. You can play where is Emmy. I have two guesses, looking at the photo, not in the front, with these ladies. I don't think they were mathematicians, all of them, no? But here in the crowd, there are a couple of faces that may be Emmy. Here is a photograph with the always surrounded with the young students and postdocs, lots of people visiting Grothendieck and interacting with Emmy. And then the disaster came. No? The disaster came. So she, on September 1933, she receives a letter saying, okay, that you have to leave the university because all Jews are expelled from university. No? With immediate no salary till it was beginning of September, no salary, not even your small salary, no. So September is the last one we are going to pay. You know? So this is expelled from math physics faculty. They were expelled actually, here are 4 names, but after all, many people had to leave because maybe they were not Jews, but they were, for example, they were married with Jews or have relatives. So Landau also have to leave, Hermann Bale. I mean, up to 17 people left Göttingen. So actually, that was a big hit, no, to the faculty. No, so that was a real. Yeah, well, okay. We all know what happened. So but fortunately for Emmy, she was well known, no. So, and she received this invitation for this woman college in Bryn Mawr, in Pennsylvania, next to Philadelphia, to work there. And okay, this is the translation actually of the letter of acceptance. This is This is the invitation. No? She had engaged first to spend 1 year one semester in Oxford, no, and after that she goes to Bryn Mawr, no, and actually even was a new for the New York Times, no, so that was very, no, that the Americans were very receptive to all these university professors, no, that had to leave, no? So that was the thing. Okay. Okay, from 1934, she's at Bryn Mawr, so commuting, and with the opportunity also, this is close to Princeton, with the opportunity to easily commute to the Institute of Advanced Studies, no? And then here is a description by a student there, no? She was not a mathematician, no? Or how her classes was, no? So Ms. Noether's classes were not lectures, they were discussions. Proofs were sometimes presented by us and sometimes suggested by Ms. Noether. The strange phenomena, as I look back on it, is that she was one of us, also as she too were thinking on the theorems for the first time. There was a lot of interest and competition, and Ms. Noether urged us on, challenging us to get our nails dirty, to really dig into the underlying relationships, to consider all problems from all possible angles. it was this way of changing perspective that finally hit home. No? So she was successful. And then there's some more sentences. She asked, Ms. Noether's methods of working and thinking became the basis of my analytical work at the research agency of Pennsylvania State Legislature for almost 30 years. No? So that's very particular way of teaching. So she was, I think from our standards, she was very bad professors, no? Because she was she was not really lecturing, they were proposing discussion, and okay, it was a mess, no? So the people that, as this one, no, that liked it, they really were enthusiastic, no? But also there were many people not liking that at all, no? That was very, but so there was not intermediate part, no, of that, but altogether they say it was very, very nice person, no? And this quality of being like one more of the group, of the class, no? So very close to the students. Okay, and here comes also so that's, no, in April 1935, she's diagnosed some pelvis cancer. She goes through surgery. It seems that the surgery had gone well, but suddenly, 2-3 days after the operation, she dies. No? That all of us surprised. No? So then Einstein wrote an obituary for her at the New York Times, which is a famous one. Here you have, I think I should stop, no? Sorry about the time.
Yes. But well, I let you finish because it's very interesting, this, but
sorry.
We have a couple of minutes.
So you can if you Google Einstein obituary, then you will find it, and you will find the text, which is very nice for her, no? And actually there are lots of texts, no? So that was, no, hope you liked the talk and you are eager to learn, and there you will find lots of things about her on internet and on the literature, so you can, if you want to learn more about these topics, is okay. So here, as I was telling Anna, so this is a bronze, some artists that I think it's nice because here, apart from the image of Emmy, no, so here we have something related with the Noether theorem, and here we have something Noether with the algebra, no, the ACC, the ascending chain condition of ideals, no, that's what the thing I find like every day on my desk, and you can see behind me in my blackboard, no? So that's all what I wanted to say. Sorry that for the rise at the end.
Okay.
Should I stop share maybe? Or...
Yeah, it's fine. So thank you, Dolors, for this talk. And you made me remember the polynomials and things about mathematics I already had forgotten. But the life of Emmy was really interesting. And also the fact that she was...
go to read more. So if it's interesting, yes.
Yeah, I see that there's a lot of documentation. I really like to see the old letters and things about it. And yeah, it's very nice that you showed us a little bit more about her life and her field of work. I don't know if there are any comments. I don't see any. There's no comments, but well, it's good because at 1 we have the other activity now about the League of Women Scientists. If you haven't inscribed, I put the link because now we change session. So there is a link on the chat. We have been more than 50 people today. So yeah, very happy for it. I don't know, thank you, Dolors, for the talk, and see you soon.
Okay, yeah, sorry for the technical things with moving the slides, but okay, well, that I will improve.
Don't worry, it was fine, and the images were very good. So yeah, thank you all for being here, and see you now in the other session with the League of Women Scientists. You can also come, Dolors, if you want to join us.
Okay, thank you. Bye.
Okay, bye.
Thank you to everybody. Yeah.
Thank you.